Section: Introduction. In this section, we introduce our exploration of large language models, LLMs, that primarily use the transformer architecture. We note that as the size of these models increases, so does the size of their input embeddings, which still represent only a single token. For instance, in the Llama models, the embedding size grows from 2048 in the 1 billion parameter model to 16,384 in the 405 billion parameter model. We find it interesting that a 2048-dimensional vector can theoretically hold enough information to represent about 1,931 tokens from a vocabulary of 128,256. This leads us to investigate whether LLMs can better utilize the capacity of these input vectors to encode multiple tokens or even entire texts. We recognize that encoding multiple tokens into a compact representation has been a challenge in natural language processing. Techniques like sentence embeddings and text autoencoders aim to capture the essential meaning of texts in a dense form. In LLMs, efficiently encoding prompts and long contexts is crucial due to the high computational cost associated with the self-attention mechanism. Some studies have looked into replacing token-based prompts with fewer dense vectors, which can significantly reduce the input length and computational requirements. These methods have shown impressive compression ratios, but lossless compression remains limited. We also highlight that embeddings serve as the operational space for the model's computations and can function as memory in certain architectures. Recent approaches have leveraged high-capacity embeddings for complex reasoning tasks directly in latent space. Understanding the latent capacity of input vectors is vital for improving how we encode and retrieve contextual information and enhance reasoning in LLMs. In our work, we investigate the limits of input representations and their ability to encode and reconstruct long text sequences. We aim to quantify the additional information these vectors can capture, providing insights into the efficiency of latent representations in LLMs. Our main contributions include: 1. An empirical study of the capacity limits of LLM input representations by compressing texts into trainable vectors. 2. Establishing a link between the latent capacity of input vectors and text cross-entropy, offering a measure of the information each vector can hold. 3. Demonstrating that capacity limits are consistent across various text lengths and types. 4. Introducing metrics that separate the capacity of trainable input vectors from the model's prediction abilities, showing a nearly linear increase in compression capacity with the number of vectors. We also provide our code for further exploration. In the related work section, we note that while compressing LLM contexts into shorter sequences is being actively researched, there is still no standardized terminology or methodology. We discuss various approaches to context and prompt compression, highlighting their effectiveness and the trade-offs involved. Our work applies a per-sample optimization process to explore the fundamental limits of compression, aiming to establish upper bounds that surpass previous findings. Section Summary. In this section, we explore the latent capacity of input embeddings in large language models, LLMs, to encode and reconstruct long text sequences, revealing that these embeddings can significantly compress information while maintaining critical details. We also establish a connection between the latent capacity and text cross-entropy, demonstrating nearly linear scaling of compression capacity with the number of trainable vectors, which enhances the efficiency and expressiveness of LLMs. Section: LLM-based lossless compression pipelines. In this section, we explore the use of language models for lossless text compression. We introduce LLM-zip, which enhances standard compression by ranking candidates based on the likelihood of the next token, and fine-zip, which speeds up compression through fine-tuning and better context management. We assess the theoretical potential of language models in compression by measuring bits per token across a representative text collection, linking compression rates to model performance through various benchmarks. Unlike previous methods, we focus solely on the language model for lossless compression, providing both theoretical insights and practical examples of compression limits. We also examine the use of trainable input tokens in different contexts. Some approaches utilize memory tokens for additional representation, while others use global tokens to improve long-range information flow. We investigate trainable soft prompts as an alternative to fine-tuning model weights, analyzing how much we can alter model behavior with these tokens. Our method involves compressing a sequence of tokens into a small set of memory vectors. We analyze how many tokens can be stored and decoded from these vectors. Our trainable memory vectors, inspired by memory transformers, are designed to encode an entire text sequence. We adopt a training method from prompt tuning, optimizing a set of special input embeddings while keeping the language model's parameters fixed. Given a sequence of tokens, we prepend a set of trainable vectors that are optimized to encode the entire sequence. During training, the fixed language model uses these vectors along with the token sequence to predict the next token. We optimize the memory vectors by minimizing the prediction error. Each text sequence is linked to a unique set of memory vectors, and during inference, we start with these learned tokens to generate the text. We aim to determine the upper limit on the number of tokens that can be generated from a single input vector. The input vector's information content is based on its dimensions and the number of bits per element. We define metrics to quantify the capacity of these trainable vectors in terms of the information they can encode and decode, focusing on reducing uncertainty in the generated text. We define several metrics. 1. Decoding capacity. In tokens, this metric indicates the maximum number of tokens that can be accurately reconstructed from the memory vectors, defined by the longest sequence length that meets a certain accuracy threshold. 2. Token gain. This measures the additional tokens that can be correctly decoded with the memory vector compared to the language model's baseline performance without it. 3. Information gain. This quantifies how much the memory vector reduces uncertainty, measured by the difference in cross-entropy when decoding with and without the memory vector. Together, these metrics help us characterize the capacity of the trainable input vectors in terms of discrete tokens and entropy, while also providing an upper limit on the length of text that can be accurately reconstructed. We compute these measures over a curated set of texts to obtain reliable estimates, noting that the absolute values of information gain depend on the vocabulary used and should not be directly compared across different models. Section Summary. In this section, we explore LLM-based lossless compression methods, highlighting our approach that utilizes trainable memory vectors to encode text sequences without relying on external algorithms. We define metrics such as decoding capacity, token gain, and information gain to quantify the efficiency and limits of our compression technique, demonstrating its potential through theoretical insights and practical applications. Section: Experiments and Results. In this section, we evaluate the ability of trainable input vectors, which are the same size as the input embeddings, across various language models using texts from different sources. For our models, we utilize those from the Pythia suite, including sizes of 160 million, 410 million, 1.4 billion, and 2.8 billion parameters, as well as OPT 1.3 billion, OLMO 1 billion, Shared Llama 1.3 billion, and Llama 3 models with sizes of 1 billion, 3 billion, and 8 billion. A complete list of these models, along with links to the Hugging Face Hub, can be found in the appendix. Regarding our data sources, we use the PG19 dataset, which contains books from the Project Gutenberg library. Since PG19 is publicly available and likely included in the pre-training data of many language models, it serves as a good reference. Additionally, we collected fanfiction texts from the AO3 library, published after October 2024, to evaluate compression on texts that models have not seen before. The details of this collection process are also in the appendix. Both PG19 and fanfiction consist of natural language texts, allowing language models to predict tokens based on context and model parameters. To focus solely on the capacity of the trainable input vectors, we also generated random texts by sampling words from the top 100,000 words in the GloVe vocabulary. We train a set of M vectors that are added to the model's input, typically using just one trainable vector unless stated otherwise. When examining the decoding capacity of a single token, we find that one trainable vector can help language models generate surprisingly long and targeted text sequences. We estimate the decoding capacity in tokens for 50 texts from PG19 across various lengths, setting a token-level accuracy threshold of 0.99. We evaluate lengths ranging from 64 to 3072 tokens. Our results show that LLAMA 3.1 to 8b can accurately reconstruct texts of up to 1568 tokens from just one input vector. Among models with around 1 billion parameters, we observe a compression capacity between 128 and 512 tokens. Interestingly, Pythia 2.8 billion, despite being larger, only achieves a compression of 128 tokens, which is less than the smaller 1 billion models. In our analysis of memorization, natural language understanding, and episodic memory, we find that generation from the memory vector combines information from both the pre-trained model and specific text sequences. We use token gain to measure the additional tokens predicted correctly and information gain to show the reduction in cross-entropy when decoding from the memory vector. Unlike decoding capacity, these metrics help isolate the contribution of the memory vector itself. We evaluate decoding capacity for PG19 and fanfiction texts across the same length grid. Our findings reveal two main observations. The metrics for both PG19 and fanfiction are quite similar across all models, suggesting that the presence of PG19 in the pre-training data does not significantly enhance performance. This indicates that compression does not rely on direct memorization of the dataset. Notably, even with random texts, larger models like LLAMA 3.1 to 8b still demonstrate strong compression capabilities, reconstructing sequences of up to 792 tokens. This highlights the effectiveness of learnable input embeddings in guiding language model generation. Ultimately, we conclude that the model's compression ability is not dependent on familiarity with specific texts or natural language knowledge from pre-training. Rather, the single trainable vector itself offers substantial capacity for storing entirely new texts or random word sequences. Section Summary. In this section, we evaluate the capacity of trainable input vectors across various language models using texts from the PG19 dataset, fanfiction, and random sequences. Our findings reveal that a single trainable vector can effectively guide the generation of long text sequences, demonstrating that the model's compression ability relies on the vector itself rather than prior knowledge of specific texts or natural language understanding. Section: Sensitivity of compression to text complexity. In this section, we examine how the complexity of input text affects the decoding ability of language models. We analyze how compression influences the model's uncertainty about the text. For our study, we selected 50 text samples from the PG19 dataset at various lengths, ranging from 8 to 1568 tokens, and up to 3072 for larger models. We measured cross-entropy before and after compression. Our findings, illustrated in a figure, show a linear relationship between the cross-entropy values for texts that are not easily compressible, indicating a consistent information gain. Texts with cross-entropy lower than the model's information gain can be perfectly reconstructed. We also tested random word sequences and found a similar trend. As long as the cross-entropy remains below a certain threshold, perfect reconstruction is possible. Interestingly, these random texts closely follow the same linear trend as the PG19 texts, suggesting that the compression principles apply universally. Thus, the memory component acts as an episodic memory, storing specific sequence information independent of the model's language knowledge. Next, we explore how compression scales with the number of input vectors. We used the same training approach for different numbers of trainable vectors, ranging from 1 to 16 for the LLAMA 3.2 to 1b model and from 1 to 32 for Pythia 160M. The results indicate that the capacity for input vectors scales almost linearly with the number of trainable memory vectors. This trend is consistent across all capacity measures, whether in tokens or text entropy. For instance, Pythia 160M can decode texts up to 2016 tokens long using 32 memory vectors, reaching its maximum context length. Similarly, LLAMA 3.2-1B can perfectly reconstruct sequences up to 7,168 tokens with just 16 input vectors. However, LLAMA 3.2-1B's scaling behavior deviates from linearity, hinting at inefficiencies in compression or limitations in utilizing more input vectors. Based on these trends, we estimate that a text like The Hobbit could be compressed into only 128 input vectors with llama-3.1-8b and 256 vectors with llama-3.2-1b. These results show that increasing the number of trainable memory vectors significantly boosts compression capacity, with minimal computational overhead for longer text reconstruction. Finally, we assess how effectively each model utilizes its input embedding space by comparing the actual capacity in tokens to a theoretical maximum based on embedding and vocabulary size. We define capacity utilization as the ratio of these two values. Our analysis reveals two groups among models with around 1 billion parameters. Older models like OPT and Pythia exhibit lower utilization, while newer models like Llama and Olmo show higher utilization despite having the same theoretical capacity. This suggests that the quality of pre-training affects how well a model can leverage its input vector capacity. For Llama models, both the 3B and 8B variants have the same theoretical capacity, but the 8B model demonstrates significantly better utilization, likely due to enhanced language understanding from pre-training. Interestingly, for Pythia models, we observe that as model size increases, capacity utilization decreases, indicating potential undertraining. In contrast, Llama and Olmo models maintain higher utilization. We hypothesize that capacity utilization could be a useful indicator of pre-training effectiveness and could inform future training efforts.